Welcome to the video on piecewise defined functions. Let's start by looking at some basic inequalities and some vocabulary that we're going to need for this video. Here's an inequality. For the right frame of mind for this lesson, it's important to understand that this is a true statement, for example, when x is 12, because 12 is greater than 5. But it's also a true statement when x is 5, because 5 greater than or equal to 5 is a true statement, because 5 equals 5. Here's another inequality. Notice that it's true when x is 3, because, of course, 3 is less than 8. But it's also true when x is 8, because the statement 8 less than or equal to 8 is true, because 8 equals 8. Here's another inequality. Notice that it's true when x is 10, but it's false when x is 4, because 4 greater than 4 can't be true. A number can't be greater than itself. Here's one more. Notice that this is true when x is 2, because of course 2 is less than 7. But notice this is a false statement when x is 7, because 7 can't be less than 7. Now, just to add some vocabulary here, these two inequalities are called strict inequalities. And these two are called compound because they have the equal sign embedded in them. Let's look at a function with two formulas. Here's a function. I've decided to call it g. And notice that it has two formulas in it. What if we were asked to find g of 3? Remember, this means that we have an input or an x value of 3, and we want to use the rules of the function to determine the output. Well, according to the rules of this function, if x is any number lower than 4, then we're going to use the first formula. Well, 3 is lower than 4, so we're going to use x squared to compute the output value. Plugging in 3 to that formula gives us 3 squared, which is 9. So notice, to find the value of g of 3, we didn't use both formulas, because the instructions guided us to one of those formulas. Let's take a look at g of 7. Remember, this means that we have an input value or x value of 7, and we're going to compute the output value using the formulas. But the directions of the formula say if x is any number 4 or higher, to use the second formula. 7 is definitely qualified as 4 or higher, so we'll plug 7 into the second formula. That gives us 12. And 12 is the output value associated with the input value of 7. So you can see so far that based on the value of the input, we're either going to use the formula on the left or the formula on the right. Finally, let's look at g of 4. I'll pause while you decide which formula you think we should use to find the output. Well, if you thought the second formula, you were right, because the directions in the function tell us if x is any number 4 or higher, then use this formula. Well, 4 technically qualifies as 4 or higher, and therefore we're going to use x plus 5 to compute the value. So I've plugged in 4 to that formula, and I got an output value of 9. Now, these functions are pretty simple to use. You just follow the directions to determine which formula you should use as an output. But there's a complication. We don't write functions this way in mathematics. They're too wordy. They take up too much space. They're very clear, but they're cumbersome. So over the centuries, the notation has gotten smaller and smaller and smaller. And now we've condensed them down over time into this. It would be worth your while to pause the video and convince yourself that these two representations, you may see them in green and purple, these two representations are the same. Hit pause if you need to convince yourself of that. And so we won't use this format in this lesson, nor will very many of your professors or teachers that you have. It's not a notation that's used anymore. So the function you see on your screen is the way that you have to train your brain to see piecewise defined functions. The piecewise defined function is just a function defined over separate intervals or in pieces. So when you see one of these things, have the proper mindset. Watch the function in the middle. Train yourself to think of, if this statement is true, or depending on which of these two statements is true, then use the formula that goes with that statement to compute the output. Now let's take a look at a process of graphing the piecewise defined function. Here's an example. If I were to graph this function, the very first thing that I would do is try to imagine what the graph of just the first formula would look like if it were its own function. In other words, I just want to consider what the graph of y equals negative 2x plus 3 looks like, and disregard the rest of the piecewise defined function. Well, this is what that graph looks like. Pause if it's been a while since you've graphed and convince yourself that that's correct. Now, according to the piecewise defined function, I'm only supposed to keep those points for which the x value is less than or equal to 1. Well, out of all the points on this line, if I'm only supposed to keep those points whose x coordinate is less than or equal to 1, then I'm going to have to erase part of this line. Notice I've erased part of the line, but I've kept all points whose x coordinates are less than or equal to 1. I'm also going to put a solid dot at the end of this half line, if you will. Now that solid dot means that this point is on the graph. Well, it should be on the graph because it has an x coordinate of 1, exactly 1. And therefore, it's part of the first line of the piecewise defined function in the sense that if x is less than or equal to 1, those points are on the graph. Now, most professors or instructors will tell you that the reason we have a solid dot there is because we have a compound inequality here. And while that is true, it kind of misses the point. Follow me on this logic. If a solid dot means this point is on the graph, then why don't I put a solid dot here? That point is on the graph. This point is on the graph, as is this one and this one. There are a lot of points on this graph. And why don't I have solid dots there? It wouldn't be wrong to do that. This is actually correct, but it's confusing. So I'll erase them, because even without the solid dots overtly written there, it's clear that we intended those points to be on a graph, because we drew a line there. So while solid dot means this point is on the graph, I don't need to put a million solid dots on my graph. Just drawing a line means the same thing. But if this dot here at the end of the line weren't there, it would leave the reader wondering, is the very end of this included in the graph or isn't it? And because I have a compound inequality there, in other words, because this is the point whose x-coordinate is 1, then I'm going to put a solid dot to indicate that that point is on the graph. Well, I'm now half done graphing this piecewise defined function. I've found all points for which x is less than or equal to 1. But now I have to graph the other function, or the other piece of this function, I should say. So for a moment, I want to pretend I'm graphing y equals x minus 2 and not think about the piecewise function at large. This is what the graph of y equals x minus 2 looks like. Pause if you need to remind yourself the basics of graphing. But according to the piecewise defined function, I shouldn't leave that whole thing there. I should only keep those points whose x-coordinates are greater than 1. So I'm going to erase part of this line that I've just drawn. You may see it in red. If I'm only supposed to keep the x-coordinates, the points whose x-coordinates are greater than 1, then I'll erase as shown. But what I'm going to do now is I'm going to put an open circle here. This open circle means this point is not on the graph. That point has an x-coordinate of 1, that open circle, I should say, and therefore I'm not keeping it because according to the instructions on the piecewise defined function, I'm only keeping the points on that portion for which x is greater than 1. But 1 isn't greater than 1, so I'm not keeping that point. Most professors will tell you that we put an open circle there because we have a strict inequality. And while that's true, it once again misses the overall picture. So follow me on this logic. That point's not on the graph, that point's not on the graph, that point's not on the graph, and that point's not on the graph, for example. There are infinitely many points that aren't on this graph. So if open circle means this point is not on the graph, why don't I just cover the whole graph with open circles and of all the points that aren't on it? Well, because it's confusing and unnecessary. You see, without those open circles there, no one would have thought you intended those points to be on the graph in the first place. So putting a bunch of open circles everywhere is technically correct, but very confusing. But if I were to leave off this open circle, it would leave the reader wondering, is that point on the graph? So we clarify for the reader by putting an open circle, saying this point isn't on the graph, but all the other points on the ray, you may see it in red, are on the graph. And that's the basic process for graphing a piecewise defined function. We don't typically write the individual pieces of the function on the graph. And we also don't typically do these in color, so we do them all in the same monochrome. And that's the answer to the graph of this piecewise defined function. Let's take a look at one more example before we go. If I'm going to graph this piecewise defined function, first I'm going to graph the first equation as if that were the only function. That graph turns out to be a parabola. Pause if you need to remind yourself how parabolas are graphed, which is not the main point of this video, but that is the graph of y equals 4 minus x squared. But I'm only supposed to keep those points whose x-coordinates are less than or equal to 1. So I'm going to erase part of this parabola. I'll pause while you try to envision what I'll be erasing. Remember, I'm only going to keep the points whose x-coordinates are less than or equal to 1. There, I've kept only those points whose x-coordinates are less than or equal to 1, and because I also want to keep the point whose x-coordinate is 1, I'll put a solid dot here to indicate that I am keeping that point whose x-coordinate is 1. Now let's graph the other piece of this piecewise defined function. Y equals x minus 2 looks like this, of course. But I'm only keeping the portions of the graph whose x-coordinate is greater than 1. So I'll erase this part and put an open circle there to indicate that I'm not keeping the point whose x-coordinate is 1 at the end of that ray, but I am keeping the rest of it. Again, we don't often write the pieces of the piecewise defined function on the graph, and it's more appropriate to use one color or no color at all. And that completes the lesson on graphing piecewise defined functions.